Okay. So last Thursday we have shown for an absolutely integral complex all real value functions over the whole real line, which is piecewise continuous on any finite subinterval of the real line, and has the left-hand derivative and right-hand derivative at every point in the real line. We can express the average of the left-hand limits and right-hand limits, right, at every point in this open interval can be expressed by such a limit, right, of integrals here. And we have let delta W to be pi over L. So you can see as L goes to infinity, then this delta W will become differential. Okay. So now we will show that so we next the right-hand side of the above equation can be replaced by the limit. So the right-hand side can be replaced by the limit okay. The reason is that for here, if delta W is quite small, then half of delta W and V will be quite small. Okay, and the approximation. So the hint is that the sign okay, so we know that the sin theta is approximately equal to theta, right? So so we have so 2 times this one would be okay. So that is the idea. Okay, what is the idea? All right, and to show that these 2 limits actually are equal, we consider a function gv. So the gv would be minus okay. So you okay. So this function is a continuous. It's a continuous function on R with G0 equal to 0. Okay. So so you can check that even though when V is 0, this is undefined. This is undefined. But when we take the difference, right? And indeed, G0 is equal to 0. You can use the L'Hopital rule to prove it. Okay, so I leave this fact for you to check. Right. So this is a continuous function, and G0 is equal to 0. Okay. So that is bounded. Okay. So this function is bounded on this finite cross interval. Okay. By the extreme value theorem, right, in calculus. So if we have a function which is continuous on a finite cost interval, then you will have extreme values. Okay, you have a maximum and a minimum value, and so that there exists an m greater than 0, such that GV is less than or equal to m for all v in the cross interval. Okay. And also, since f of x is absolutely integrable over R, so we have, you can see that so let's see, minus L minus x, and f of v plus x, okay, and the gv. Okay, so we consider this integral. Okay, all right, and because gv has an upper bound in this finite cost interval, so we have okay, and so it's finite. So it's okay. So you can see that because we integrate over the whole real line, so this is indeed an upper bound. Okay, so from here, so that f of u plus x and gv is absolutely integrable over this finite cross interval. Okay, so by the Riemann-Lebesgue lemma, so we have, okay, so we had a limit n goes to infinity at minus x okay, so this is GV, and here, okay, this is f of that, and the sign this numerator m plus 1/2 becomes to be 0. Okay. So GB, and so this product is absolutely integrable, right? From this checking, and so this product multiplied with this sinusoidal signal, okay. And for n goes to infinity, then this is 0. Okay? Is that clear? And you can see this limit is just the difference of these two limits. Okay. Okay, so look at that. Okay, so this limit can be replaced by this limit because they are equal. Okay, because they are equal. Any questions? Now, so now here we can. So once we establish this identity, now we can cancel. Okay, so now for all x, so now for any fixed x in the okay, so we have equal to limit okay. Now we check to see if things. Now we will so this integral. We look at the integral, but you can see that the limit, upper limit and lower limit of this integral depends on x and L, right? So now we check. We will amend, extend the limit of this integral. So now we check from L minus to infinity, and okay. So we look at that this function is absolutely integrable over this extended interval, this semi-infinite interval, right? So we will want to see that. And this is L minus x. Okay? Because v is from L minus x to infinity. So the smallest v would be L minus x. Okay? So 1 over v would be less than or equal to 1 over L minus x. Okay. And this again, this is finite. So this shows that this one, okay? So we check this one and check the other minus L minus X to minus infinity. Okay, and again, you see that this is equal to L plus X. Okay, and right? So that the 1 over the absolute value of V on this range, you can see that the biggest one would be this number. And again, so we have that. Now with that, F divided by V is absolutely integrable over L minus X infinity and over okay. So that we can apply Riemann the Bag lemma to show that the limit n goes to infinity L minus X F plus X V sine n plus 1 of delta V dV is equal to 0. And the limit also equal to 0, right? Okay. By Riemann the bag. Again. Okay, so this is 0, right? And so we add these two limit to here. So now okay, so we add these two limits to that limit, right? So now, so we have divided by 2 is equal to the limit n goes to infinity. This is so the integration limit will be from minus infinity to infinity V sine n plus 1/2 and delta W. Okay, and by change of variable, I forgot to put yeah. Okay, sorry. 1 over pi. So that 1 over pi. And this limit would be fu u minus x and the sine m plus 1/2 and du with the change of variable, that's u equal to v plus x. Okay. All right. And now things this function is actually the integral cosine u minus x dw. Okay. So okay. So this integral actually is this integral. For any fixed x in minus L. So we have, so now we have f of x minus plus of x plus divided by 2 is the limit of n goes to infinity 1 over pi fu and m plus 1/2 delta w0 cosine w u minus x and dw and du. Okay. Now the integration. All right. So we need a theorem to exchange the order of integration. Okay, because in this integral we integrate over w and then over u. Okay. So we need a theorem of interchanging the order of integration. Okay, and so I quote a theorem, and in the literature, and summarize in this theorem, interchanging the order of integration. Okay, so I, j to be two subintervals, right? Maybe bounded or unbounded, maybe closed or open, or half open, half closed of the real line, right? And k of xy is complex or real valued function. Okay? Which so it has two arguments, right? And which it's continuous and bounded. i.e., we assume kxy less than m for all xy in the Cartesian product. Okay, for some constant m greater than 0, right? So this is our conditions. Now we assume that f and the g are absolutely integrable over I and j okay, maybe I write here fx gx gy, so they are complex or valued function. Okay, sorry. They are absolutely integrable complex real over I and j respectively. Okay. All right, so f of x is absolutely integrable over I, and g of y is absolutely integrable over j. All right, so with this, then we have A for each fixed y in j, okay, f of x, k of x, y. Right, so when y is fixed, then kxy is a function of x over I, right? So this product is a function of x. So this product is absolutely integrable over I. The reason is that this function is bounded. Okay, this function is bounded, so that it's integral over I, and the function fy defined on J by the equation fy is the Okay, so this is the since this product is absolutely integrable, so this integral exists. Okay, so for each y, this must be a complex or real value. This a common number or real number. Okay, and so it's a function. All right, it's a complex or real value function defined on J, and such a function is continuous on J. Okay, so such a function is continuous. Okay. Remember, the kernel, the k function, the kernel function, is continuous. Okay, and bounded. Yeah. This is the reason why that this has become to a continuous. Right. So this is a part. B part. Now, for each fixed x in I, gy, k, xy. So now, if x is fixed, then this product is a function of y, and this function of y is absolutely integrable over J, and the function gx defined on I by the equation g of x equal to gy kxy dy is also continuous on I. Now part C. Now f of x and the capital G of x, this integral, and G of y, capital of x of y, are absolutely integrable over I and j respectively. And now the integral f of x, g of x, d of x over I here will be equal to g of y, f of y, dy over j. Okay? And if we expand the definition of capital G and capital F, we will see that that would be equal to so that means that we can exchange the order of integration. So this is a very general theorem that you can use this theorem not only in this course but in everywhere else. Okay, in the future, if you need to consider the interchanging of the order of integration, then you can check the premises. So there will have 3 premises, right? So ij, the interval can be arbitrary, right? So the interval ij can be any subinterval of the whole real line, and the kernel, the requirement for the kernel kxy would be continuous and bounded, all right, on this Cartesian product. So it should be continuous bounded. So you need a continuous kernel and bounded kernel. And f and g can be arbitrary, absolutely, all right, arbitrary, absolutely integrable functions, okay, over I or over j respectively. Then we will have this. So the change of integration is valid. Okay, so you can see, you can integrate. So the kernel will be fxgy and kxy, right? And then you can integrate over y first and then over I. Or you can integrate over I first and over j. So you can change the order of integration. Okay, and so now we go to here to check the kernel. So what is our kernel? Okay, so so to apply theorem 11.7.a, discussion. We observe first, okay, that so, okay, so what we have is here. So we see that we have I equal to j equal to from 0 to n plus 1/2 delta W. Okay, and the f of u is equal to second, and k of u w is equal to cosine w u minus x Okay? Is defined on I and J. Third one, Fu is absolutely integrable over I and G of W, which is equal to which is equal to 1 x absolutely all right. This function is continuous and bounded on okay, because cosine function is continuous, right? And bounded, of course, bounded by 1, right? Cosine function bounded by 1, so it's continually bounded. Fu itself is absolutely integrable. And where is G? Well, GW, maybe I use H, okay? I use H. HW is 1, right? 1 here, HW 1. So it's also absolutely integrable over J, which is from, okay? This is finite interval, so the constant function is absolutely integrable. Okay, so now let's see the 3 conditions. So okay, the kernel is continuous and bounded, no problem. F and G, now F and H, they are absolutely integrable. Okay? Right. So that's so now the integral so now F of U H of W cosine U. So now I just, because it's 1, so I just write it. And so this becomes 2 and half and 0. And here would be Fu and the cosine W minus X and du and dw. Okay, so we now we exchange the order of integration. Okay, and so that f of x plus divided by 2 becomes to the limit n goes to infinity 1 over pi and from 0 cosine w u minus x and the d u dw. Okay, And now that when n goes to infinity, this goes to infinity. So this is just equal to 1 over pi from 0 to infinity. And the f of u cosine u minus x du and the dw. Wow. So as you can see, that the dependence of L disappeared. All right, so this is true, okay, for all x in. All right, so this is true. All right, so by letting L goes to infinity, now we have so that f of x minus plus f of x plus divided by 2 is equal to one over pi fu cosine omega u minus x du and the dw for x in R. Okay? So this is a nice formula we have. All right, so this is crucial to have this identity. Okay. All right, and the rest of the chapter will depend on this formula. Okay, depend on this formula. So now we look at the inner integral. Cosine u, and where we have cosine u and the cosine wx plus sine w sine wx and du. Okay. So now, so this is independent of u, right? So we can split this into sum of two integrals. Cosine du cosine wx plus sine w du and sine wx. Okay. All right. So we have that. And now we define this one to be a w and define this integral to be BW. Right? Then AW, which is 1 over pi, I'm sorry. No. We need 1 over pi. So define. I'm sorry. I use define A W to be 1 over pi U and B defined to be 1 over pi sine. Okay. All right. So we define two functions, which, all right, so which are continuous. Okay. We are continuous function on 0 to infinity. Okay? 0 to infinity. Or this is because that the W is range from 0 to infinity. Okay, so you can think about W to be angular frequency. Okay, so it's from 0 to infinity. Right? So they are continuous function, right? By an application of theorem 11.7.a. So you can apply A. Okay, because this function, so use suitable kernel, so you can use the kernel to see this is continuous. Okay, so here the kernel would be cosine W. Okay. All right. So when kernel UW to be when the kernel, so here you can think about the kernel of UW. It's okay. U and here the kernel you are using is sine W. Okay, you can use this to kernel, right? And to apply, so for here, and then apply theorem 11.7.a and the little a part, then it is continuous. Okay, so both A and B are continuous functions. Okay? And it is interesting to know that the limit of omega goes to infinity, A omega is 0, and the limit of B W goes to infinity is also 0. All right, by the Riemann-Lebesgue lemma. Okay. because f of u is absolutely integrable over the whole real line. And this is simultaneous signal, right? So when omega goes to infinity, this is go to 0. Okay, so we have these two results because of the Riemann-Lebesgue lemma. Okay, so now we can state sorry. So we can state the main theorem. So now theorem 11.7.1. So this is called the Fourier integral theorem. So if f of x is absolutely integrable over the whole real line, complex or real valued function on the whole real line, which is piecewise continuous on any subinterval, finite subinterval of R, and has the left-hand derivative and the right-hand derivative at every point in R. Then f then that we can write a omega cosine x plus b w sine of x dw or x in R with a w is equal to 1 over pi cosine and okay. So this is called the Fourier integral theorem. So if f is continuous at x, then the average is equal to the f of x. So the f of x can be expressed by such an integral. Okay. So this integral is called the Fourier integral. Okay. Associated with f. Okay. Right. Okay. So I think I stop here.